This is part 2 of lecture 4.3, functions. In this video, we will consider the inverse of a function and the composition of functions and look at their properties. We begin with the composition of two functions. For any functions f from a to b and g from b to c, the composite relation gf is a function from a to c. To prove this, we will show that for any element x in A, there is a unique element z in C such that the ordered pair xz is an element of GF. Let x be an element of A. First, we show existence. Since A is the domain of F, there exists an element y in B such that the ordered pair xy is an element of F. Since B is the domain of G, there exists an element Z in C such that the ordered pair XZ is an element of G. Thus, the ordered pair XZ is an element of GF by the definition of the composite relation GF. This proves existence. Next, we show uniqueness. Let Z and W be elements of C and assume that the ordered pairs XZ and XW are elements of GF. Then, by the definition of the composite relation GF, there exist elements Y and V in B such that XY is an element of F and YZ is an element of G. And XV is an element of F and VW is an element of G. Since f is a function, this means that y equals f of x and v equals f of x. Thus, y equals v. Also, since g is a function, z equals g of y and w equals g of v. Since y equals v, we have g of y equals g of v. So z equals g of y equals g of v equals w. Therefore, z equals w, which proves uniqueness. This completes the proof that the composite relation GF is a function from A to C. Given functions f and g, for any element x in the domain of the composite function GF, the image of x under GF is g of f of x. Indeed, z is equal to the image of x under GF if and only if the ordered pair xz is an element of GF. If and only if, for some object y, the ordered pair xy is an element of F and the ordered pair yz is an element of G. If and only if, for some y equals f of x and z equals g of y. If and only if z equals g of f of x. Note that in the previous theorem, it is assumed that the domain of G is equal to the range of f, and it follows that the domain of GF is equal to the domain of f. Suppose that the domain of G is not necessarily equal to the range of f. Then the domain of GF is the set of all objects x, such that for some object z, the ordered pair xz is an element of GF. This is equal to the set of all objects x, such that there exists an object z, such that for some object y, the ordered pair xy is an element of f, and the ordered pair yz is an element of z. Equivalently, there exists an object y, such that for some object z, the ordered pair xy is an element of f, and the ordered pair yz is an element of g. This is equivalent to the condition that for some object y, the ordered pair xy is an element of f, and for some object z, the ordered pair yz is an element of z. The first condition in the above is equivalent to the statement that x is in the domain of f and y equals f of x. The second condition is equivalent to the statement that y is in the domain of G. Hence, the domain of GF is equal to the set of all objects X, such that X is an element of the domain of F, and f of X is an element of the domain of G. In general, it is not true that if f is a function from A to B, then f inverse is a function from the range of f to A. The statement f inverse is a function from the range of f to A is equivalent to the condition that for any element B in the range of f, there is a unique element small a in the set A such that the ordered pair BA is an element of f inverse. The negation of this statement is equivalent to, for some element B in the range of f, either there is no element small a in set A such that the ordered pair BA is an element of f inverse, or such an element of set A is not unique. That is, for some element B in the range of f, either there is no element small a in set A such that the ordered pair BA is an element of f inverse, or there exist elements A1 and A2 in set A such that the ordered pairs BA1 and BA2 are both elements of f inverse, but A1 is not equal to A2. As a counterexample, consider the function f consisting of all ordered pairs xy of real numbers such that y equals x squared. It is left as an exercise to show that f is a function from the set of real numbers to the set of real numbers with range the set of non-negative real numbers. However, the relation f inverse is not a function from the set of non-negative real numbers to the set of real numbers. Indeed, f inverse is the set of all ordered pairs xy of real numbers such that x equals y squared. Take x to be 1, y1 to be 1, and y2 to be negative 1. 1 squared equals 1, and negative 1 squared equals 1. So the ordered pairs x, y1 and x, y2 are elements of f inverse. But y1 is not equal to y2. Therefore, f inverse is not a function from the range of f to the set of real numbers. In this example, R is an arbitrary relation. The composite relation R inverse R is a subset of the identity relation on the domain of R if and only if R inverse is a function from the range of R to the domain of R. The statement R inverse R is a subset of the identity relation. The statement R inverse R is equal to the identity relation on the domain of R is equivalent to the condition for any objects X and Z, the ordered pair XZ is an element of R inverse R if and only if XZ is an element of the identity relation on R. The statement R inverse is a function from the range of R to the domain of R is equivalent to the condition for any element Y of the range of R, there is a unique X in the domain of R such that the ordered pair XY, YX is an element of R inverse. To prove the forward implication, assume that R inverse R is equal to the identity relation on the domain of R. Let Y be an element of the range of R. Then, by the definition of range, there exists an element X of the domain of R such that the ordered pair XY is an element of R. Hence, the ordered pair YX is an element of R inverse. Next, let X1 and X2 be elements of the domain of R. And assume that the ordered pairs YX1 and YX2 are elements of R inverse. Then X1Y is an element of R by the definition of R inverse. and yx2 is an element of R. Rather, yx2 is an element of R inverse. So the ordered pair x1, x2 is an element of the composite relation R inverse R. Since R inverse R is equal to the identity relation on the domain of R, we therefore have x1 equals x2. This proves that R inverse is a function from the range of R to the domain of R. For the converse, assume that R inverse is a function from the range of R to the domain of R. By an earlier exercise, the identity relation on the domain of R is a subset of the composite relation R inverse R. So it remains to show that R inverse R is a subset of the identity relation on the domain of R. Let the ordered pair xz be an arbitrary element of R inverse R. Since R is a relation from the domain of R to the range of R, and R inverse is a relation from the range of R to the domain of R, this implies that there exists an element y of the range of R such that the ordered pair xy is an element of R and the ordered pair yz is an element of R inverse. So yx and yz are both elements of R inverse. Since R inverse is a function, x and z are both equal to the image of y under R inverse, and thus x equals z. Then the ordered pair xz is an element of the identity relation on the domain of R. Thus, the composite relation R inverse R is a subset of the identity relation on the domain of R. This proves that R inverse R is equal to the identity relation on the domain of R. You have come to the end of part 2 of lecture 4.3. Before you proceed to lecture 4.4, you are strongly encouraged to do the exercises given at the end of these slides. Thank you for your attention.